We're going to deal with 3 alpha. So on page 117 of the book, actually I want to go to 116. So where you're looking on page 116 of the book, you see this. Rule 1. Nobody cares about the numbers of the rules. All right? This says the derivative of f with respect to x is equal to the derivative with respect to x if the function's a constant. This is more kind of convoluted, hard to read, but it just means this. The derivative of a constant is 0. So that would look like this. If I went to y equals and I graphed a constant, say y equals 2, ready? The function f of x equals 2 all the time. The slope of this horizontal line is 0. And that's what this is telling you. The derivative of a constant is 0. Now, this is the most important thing you're going to do today. And you've been looking forward to this, whether you realize it or not. This is the power rule. And using the power rule will save you from having to do the difference quotient the long way. All right? And there's a proof in here that I'm going to try to explain to you. This proof is not understandable the way it's written in the book. Okay? But before we get to the proof, we're looking at this line right here in the book. First thing, the left side, you should recognize that is the difference quotient. The numerator is subtracting up. F of x, take away h is the input, take away f of x, over x plus h, take away x, the x is added to 0. And they're saying in this case, you have a power function. And the power function is, when you're subtracting up, you would have x plus h raised to the nth power. So what's an example of a power function? Well, the most user-friendly power function would just be x squared. Okay, you have a variable in the exponent. That's a power function. So how can we get the derivative of this? And we actually did this, x squared, using the difference quotient because it was one of the problems where the derivative did not exist, and it was x squared in quadrant 2 and y equals x in quadrant 1. So that work was there with the difference quotient. But this rule will save you from doing that. So I'm here. Now the rule, the proof is based on this, which isn't in your book, so I'm giving this to you. You can factor the difference of squares. Yes, I've done that in Algebra 1. You can factor the difference of cubes. You can factor the sum of odd powers, which we don't need for this exercise, but we can factor the difference of any exponent of any power, even or odd. And it factors into this. Right? So this is the general term, and then these two are subsets of that. So what do you get? Well, you divide out, if you had, suppose you had this, x squared take away y squared. You would divide it by x take away y, and it would give you x plus y. So this is going to give you a, the first term, raised to an exponent 1 less than n. And then the exponents of a are going to go down by 1 until you get to 0. Anything to the 0 power is 1. B is going to start with b to the 0, which is 1, and go up by 1 till it gets to b to the n take away 1. And the reason I put this up here is because we're going to show you the derivation on page 116, try and make this a little more reader friendly. Now, again, you're never going to have to produce this, but you want to be able to follow it. So this line right here is exactly what's in your book, except they use small case letters. On the fourth line up from the bottom on page 116. This line right here is this. Right here. It's this part of the proof that you can't figure out in the book because it's too abbreviated. So here's what happens. I'm going to associate this with this bottom line up here with the A's and B's. And to make it a little less cluttered, I'm going to refer to x plus h as the A and x as the B. What do you have? A to the n, subtract b to the n. So the first term is A take away B, which would be this take away this, which is x plus h take away x. Then the A term is x plus h. That starts with an exponent of n take away 1, 1 less, and you would have x to the 0. I didn't write it because it's the 0 power and I was kind of pressed for space. But as you go to the right, the exponent of x plus h goes down by 1. And the exponent of x goes up by 1. Just like it does up here in the general expansion. Next thing, these x's add to 0 and leaves you an h out here. This h is going to reduce with the h in the denominator and just leave you with this term. But this term, this sum of terms, is x plus h to the n take away 1. Now look at the next term. X plus h to the n take away 2 times x to the first. Well, you notice what's happening? When you take the limit as h goes to 0, then this would be x plus 0 to the n take away 2 times x to the first. And you have like bases, you add the exponents. So n take away 2 plus 1 would give you n take away 1. The same as this term. So you end up adding all these x to the n take away 1s. How many of them do you have? N of them. And this n, this multiplication, is a shortcut for addition. This is the power rule, which in practice is very user-friendly. You will not have to do all this work. But again, it goes to your depth of understanding if you can follow it. And all this, this is just the only thing that's hard to follow, that we couldn't have the Algebra 2 children follow, is the limit part. So we're going to example 1. Here's example 1. Ready? And again, they're using different letters. That's a good idea to kind of get you away from just using x's and y's. And in this case, p depends upon t. And you have this cubic. So you want to take the derivative of the left side with respect to the input, which is a t. And don't dismiss this notation. You have to be able to read this. The derivative of p with respect to t, well, where there's a p, I write what p equals. All of this, what's in the parentheses. So you're going to take the derivative of what's in the parentheses with respect to t. And you're just doing the power rule 4 times. You take the 3 out front, and you replace the 3 in the exponent with 1 less. So t cubed differentiates to 3t squared. 6t squared. The 2 comes out front. 2 times 6 is 12. T to the first. Negative 5/3 t to the 0. Anything to the 0 power is 1. Plus 16. The derivative of a constant 0. That's it. So this cubic is your parent graph, and the derivative is 1 degree less. It is a quadratic. Okay? This is not hard. The rest of the section may get harder, will get harder, but this isn't hard. So I'm going to leave this up here, and you're going to problem number 5, please. That make sense? The question is a cubic. Just apply the power rule to get down to this quadratic. Now, what does that mean? Well, you don't need to do this, but just look up here. I go to the calculator. There's the question. X cubed divided by 3 plus x squared divided by 2 plus x. And we'll just graph that. Now, what is this? This is a cubic third degree. How many zeros does it have? 3. How many of them are real? 3 or 1? Okay? We're going to have multiplicity of roots here, but that's not the issue. We go back here and we say the derivative would be 1 degree less. So that's just going to be x squared plus x plus 1. Now the red graph is the derivative. See if this makes sense to you. Think about something you see here. The red graph is positive over the entire domain. The red graph is above the x-axis. And what do you got? The blue graph is rising the entire time. And that's what the derivative is telling you. If the derivative is positive, the parent graph is rising. If the derivative graph grows below the x-axis, that's telling you the parent graph is falling. Now I go back here. Now remember this. This is from last week. If I turn this off, I can check my answer by turning on Y5 or Y6. Y6 is a little safer now because we don't have to worry about what value is stored in H. Here's my answer. I think that that is the derivative of Y1. The technology is going to differentiate Y1 for me. I'm going to see if they match. And the tables are the same. The tables are the same, confirming that you did this correctly and that Y2 and Y6 are the same. Y2 is the derivative that you calculated, and Y6 are the values for the derivative that the calculator did for you. Okay? Example 2. So we're on page 118. Example 2, you have this. You have 4th degree. So the derivative is going to be 3rd degree. And they're saying, does the curve have horizontal tangents? Now think about this. If the curve has a horizontal tangent, that's where the graph is reaching a minimum or a maximum. It's where the graph is falling and begins to rise, or rising and begins to fall. So in those cases, the derivative would be 0, because if you had a horizontal tangent, the slope of a horizontal line is 0. So we differentiate the question. The 2 differentiates to 0. And you get this. The greatest common factor on both sides of this subtraction sign is a 4x. When you take that out, you're left with 4x times the difference of squares. X squared take away 1, which factors into this, which you're familiar with, I hope, the squares. And now what? The derivative is a cubic. So it has 3 zeros. How many of them are real? 3 or 1. In this case, there are 3 values that make the derivative 0. -1, 0, and +1. Now, I left out the middle column of the H chart. But the point is, these are the inputs where the parent graph would have a horizontal tangent. See, this problem is meant to be done without a calculator. We can confirm it by looking at the picture, but if you look in your book, we're on example 2. And example 3 is the same type of question. It's a 4th degree where they do expect you to use the calculator. So you have to, discipline yourself. The problems that or without a calculator to make sure you can follow this. But if I just want to visualize it, and I go to the calculator and go, well, x to the fourth subtract 2x squared plus 2. There's the graph. Ready? And what did our work? I didn't want that on. And what did our work tell us? Our work told us that we had a horizontal tangent at -1. We had a horizontal tangent at 0. We had a horizontal tangent at +1. Which you can see that. Then if I go in here, and how does that work with my answer? We already know what the answer is, so I'll just turn on y6 for now. If I draw the derivative, what do you notice? The horizontal tangents occur at the input where the derivative is 0. The orange line has a height of 0. There's a horizontal tangent above it. At 0, the orange curve has a height of 0. There's a horizontal tangent for the parent graph above it. At 1, the derivative is 0. Above it is a horizontal tangent to the parent graph. Okay? So that's your model, and you're going to go to problem number 7. And you would have this. You have a cubic, all right? So if I graph this, I mean, I want you to do this work without a calculator, but we'll confirm it. Here's what the picture looks like. Okay? Now, what can you tell here? That this cubic has been shifted up. So its third degree, it has 3 zeros. How many are real? 3 or 1. In this case, we can tell that it's 1 real 0. Why? Because this graph, we move the axes up, it's going to cross the axes 3 times right in here. So shifting the graph up, which is what happened, doesn't affect its degree. So this is third degree. The derivative is going to be second degree. What do? We get 3x squared plus a -4x plus 1. I want to factor that. Well, to factor it, really, I mean, you should be able to factor this thing. It's quadratic with a lattice, which ready? I want to factor 3x squared plus a -4x plus 1. So these cells in the top have to be 1. They're the only things that are going to add to 1. These two terms add up to a -4x. So these 1s have to be negative. -1 times -1 is still 1. And what multiplies to 3x squared? 3x times x, which would give you -3x and -x. So these are the linear factors. Then I took the 3x take away 1 and factored a 3 out. You don't have to do this. You can just set 3x take away 1 equal to 0, and you'll see that 1/3 makes it 0. 1 makes this 0. Ready? These are the inputs. I'm leaving out the height of the function here and just saying when is the derivative 0, when it would have a horizontal tangent. So I take this 3x squared plus a -4x plus 1. We'll do it the long way this time instead of just turning on Y6. And what do you notice? Ready? The graph is only under the x-axis in this little amount, somewhere between 0 and 1. And what's happening to the blue graph there? It's falling. And all the rest of the time, the red graph's above the axis, and the rest of the time, the blue graph is going up. So the horizontal tangents are where? Well, this value I can now quantify because we just did the work analytically that this is the point 1/3 to the right of 0. This is the point 1, 0. And that's where this graph, the blue graph, will have a horizontal tangent. Okay? And then this question, example 3, is the same type of question where you would use a calculator. What have I got? This picture here goes with example 3. The parent graph's 4th degree. It has 4 zeros. How many are real? 4 or 2 or none. Well, you can see it's 4 real zeros. It's crossing the axis. But if you move this graph up a little bit, then you only have 2 real zeros. If you moved it up a lot, you'd have 0 real zeros.